You know the feeling. You're right in the middle of something, and then the lights flicker, and everything just dies. That sudden, dead silence. It is so frustrating, right? And it always seems to happen at the absolute worst time. But have you ever wondered what's really going on behind the scenes to get the lights back on? Well, let's pull back the curtain and dive into the incredibly complex, high-stakes world of power restoration.
So, the screen goes dark. Your house is quiet. What's the very first thing that happens? You might think someone's scrambling to flip a switch somewhere, but nope. The first response is actually automatic, happening in a split second, and it comes from the grid itself.
I'm pretty sure this sounds familiar to just about everyone. That weird on-again, off-again dance the power does right before it gives up for good. Well, that's not a glitch or the system struggling. That's actually the grid trying to heal itself.
And the thing responsible for that flickering is a pretty cool piece of tech called an automatic recloser. The best way to think of it is as a super intelligent circuit breaker out on the power pole. So let's say a tree branch just brushes against the line for a second. The recloser senses that fault, opens a circuit to clear it, and then bam, it closes it again to get your power right back on. It'll give it a few tries just in case.
But if the problem is more serious, like that branch actually broke the line and is still lying on it, the recloser says, okay, I've tried my best, this is a real problem, and it locks itself in the off position. And this is the most important part. That final off isn't just cutting the power. It's also sending an instant digital signal to a control center, telling them, hey, we have a permanent fault here. And that is the moment the human response truly kicks into gear.
All right, so that automated signal hits the control center. And what happens next isn't just a chaotic scramble. Far from it. A highly organized, almost military-style operation immediately clicks into place.
They use a framework called the Incident Command System, or ICS for short. And this is a huge deal because it's the exact same standardized system that firefighters, police, and FEMA use to manage everything from hurricanes to wildfires. An area commander takes charge, and a crystal-clear chain of command is activated. No one is wondering who's in charge. And under that command structure, the goals are not just clear, they're set in a strict order of importance. Number one, first and foremost, is life safety. That means finding and securing any downed wires that could hurt someone. Only after that's done do they move to number two, stabilizing the incident to stop it from spreading. And finally, they work on preserving property.
So, the command center is up and running, everyone knows their priorities. The next huge challenge is basically detective work. Where exactly is the physical break in the line? The hunt is on. You know, back in the day, the method for finding an outage was pretty low-tech. This quote really says it all. Utilities would literally wait for the phone calls to start flooding in. They'd get a map, put a pin in for every complaint call, and figure the problem must be just past the last pin on the line. It's clever, I guess, but not very fast.
But today, of course, technology has totally changed the game. They use something called an Outage Management System, or OMS. This software is the high-tech brains of the operation. It pulls in data from everywhere, smart meters pinging that they've lost power, sensors on the grid, and yeah, even the customer calls. And it runs all that through algorithms to predict the fault's location, often with incredible accuracy. But, and this is a really big but, that amazing tech can't do everything. A computer algorithm can predict a location, but it can't actually see a broken pole or a tree that's fallen on the wires. So you still need linemen to get in their trucks and physically drive that entire stretch of the line, inspecting every inch with their own eyes. It's this critical mix of high-tech prediction and old-fashioned boots-on-the-ground reality.
Okay, so that's for a standard outage. But what happens when something massive hits, like a hurricane or a brutal ice storm, and the damage is so widespread that the local utility is just completely overwhelmed? Well, there's a system for that too.
It's called mutual assistance, and it's this incredible industry-wide partnership. It's basically a we've got your back system. Utilities that are hit hard by disaster can put out a call for help, and other utilities from regions that weren't affected will send their own crews, trucks, and materials to help out.
And the whole process is surprisingly fast and efficient. So picture this. The affected utility figures out what it needs, say 200 extra line crews. It sends that request to its regional group. That group immediately hops on a conference call with dozens of other member utilities, who then say, I can spare 10 crews, or I can send 15. And within hours, you can have a literal convoy of utility trucks rolling down the highway from hundreds of miles away, all headed for the disaster zone.
Now, the reason this system is so vital is that it allows for this massive surge of help exactly when and where it's needed most. It's also way more cost-effective. I mean, no single utility could afford to keep a giant army of linemen just sitting on standby for a once-in-a-decade storm. This way they share the load. It's all about a rapid, scalable, and powerful response.
So, we've covered local outages and even huge regional disasters. But let's talk about the absolute worst-case scenario, a total grid-down blackout, a massive area with no power at all. How in the world do you even begin to restart a completely dead grid?
This procedure has a name, and it sounds pretty ominous. It's called a black start, and that CPR analogy is perfect. Here's the problem. Big power plants actually need a lot of electricity just to run themselves, to power their pumps, computers, and systems. So if the whole grid is down, they have no power source to even begin to restart. A black start is the delicate step-by-step process of bootstrapping the entire system back to life from absolute zero.
And it has to happen in a very specific, careful sequence. It all starts with something small, like a little on-site diesel generator. That generator provides just enough juice to start up a special, quick-start power plant, often a hydroelectric dam. That dam then sends power down a major transmission line, delivering a jump start to one of the huge baseload plants, like a coal or nuclear facility. Once that big plant is running, it can then provide the power to restart other plants, and you painstakingly rebuild the grid almost island by island.
Now, all this talk about downed lines and massive storm recovery brings up a question that people always ask, especially after a big outage. Why don't we just bury all the power lines underground and avoid these problems in the first place?
Well, it's a great question, but the answer boils down to a series of really big trade-offs. On the one hand, yes, underground lines are much better protected from wind, ice, and falling trees. That's a huge plus. But on the other hand, they have a massively higher upfront cost to install, and this is the real kicker, when they do fail, finding and fixing the problem is way more complex and takes a lot longer.
And when you look at the raw numbers, the cost difference is just staggering. For a typical distribution line, you're looking at about $1.5 million per mile to put it underground, versus less than $300,000 to build it overhead. We're not talking a little more expensive, it's over 5 times the cost.
And then you have the repair time. Think about it. If an overhead line breaks, a crew in a bucket truck can usually spot it and fix it in a matter of hours. But if an underground cable fails, first, you have to find the exact spot, which can be tricky. Then you have to bring in heavy equipment to dig a giant trench just to get to the cable. A repair that might take a day for an overhead line could easily take a week or more for an underground one.
So this brings us right to the heart of the debate. It's not really an engineering problem anymore. We know how to bury lines. It's an economic and social one. Who pays for this massive cost increase? Does the utility just absorb it? Do all customers see their bills go way up to cover it? Or do only the people in the specific neighborhood getting the fancy new underground lines foot the bill? There are no easy answers.
So the next time the power goes out, hopefully you'll think about the reclosers trying to fix the problem, the command center springing into action, and the linemen out there hunting for the break. But you'll also know it's all part of this giant, complex machine full of difficult trade-offs. And it leaves us with the ultimate question. The grid isn't perfect, but making it closer to perfect costs a fortune. So how much are we as a society really willing to pay for it?